It's the 18th of September, 2015, and this is episode 25 of the Unseen Podcast. This is your host, Paul Carr, and tonight we have with us Adam Synergy Smith.
Hey everyone, great to be here again.
And James Garrison.
Hello, everybody.
And okay, I'm going to do this right this time. Mateusz Macias.
Yeah, that was great, Paul. Yeah, hello, everybody. It's nice to be back.
And Nick Nielsen.
Hello again to the Unseen Podcast.
All right. Well, Nick's our short notice substitute. So thanks, Nick. I think 4 is about the right size. Now, before we get started tonight, I'd like to mention that just the last few days there have been new images coming down from New Horizons, Pluto, from the close encounter that happened in July. And they are really impressive. So if you've not seen them, by all means go to pluto.jhupapl.edu. I'll have the link in the show notes and have a look. Nothing that I want to really comment on yet, just that these pictures were taken from completely different sun angle, so they're kind of backlit, and you see the sun sort of coming over the limb of the planet and illuminating the mountains. And it's really cool. If nothing else, it's just aesthetically pleasing. So by all means, have a look at those. And we'll have more on that, I'm sure, before too many more moons pass. Also, by the way, the white spots on Ceres that we mentioned a couple of times have recently had a much higher resolution image. Doesn't solve the mystery, I don't think, but it certainly maybe rule out a few theories. So have a look at that too. Go to, I think it's, we got to write dawn.jhu, not jhu, dawn.jpl.nasa.gov, or something like that. We'll get the right link in the show notes. If you just say Dawn series in Google, it'll pop you right there. So anyway, great images. Nothing really to say about them yet, but go have a look. Okay. Now tonight we want to talk about a couple things. One is something that's been really hot lately, which has been the search for exoplanets. There have been a huge success in this latest surge of Kepler-2 discoveries, which Kepler-2 is Kepler after it was down to 2 reaction wheels. They figured out a clever way to still continue the mission. They have discovered a lot of new planets lately, and what we want to talk about tonight is kind of where it's going from here. You will continue to see many new announcements of exoplanets from Kepler, also from ground-based telescopes. Quite often the Kepler findings are followed up by ground-based telescopes. Also feel a lot of modeling going on in the astrophysics community, trying to understand how planets can get to be the way they are, how solar systems can be the way they are. And even our own solar system is still somewhat controversial. So now, Adam, there was a paper about you got to remind me, Adam. What was the first one about?
I've read a couple of papers just this week that have just been uploaded to the preprint archive.org. One of them was about no evidence for the destruction of protoplanetary disks close to huge, massive Type O and Type B stars. Good news, if you happen to live on a planet somewhere near a big star, you do exist. So,
right. I mean, I'm trying to remember a Type O star.
They're the very biggest.
They don't have terribly long lives, right? I mean, they
No.
live like 100 million years and they're gone.
Had there been suggestions that the very large stars would destroy the planetary disk around them?
That's right. Theory predicts that any protoplanetary disk within about 0.1 of a parsec should be photo-evaporated. So a team of astronomers used a combination of Hubble images and Spitzer infrared space telescope images. They looked at star formation regions containing these big Type O and Type B stars, looking for what are called proplids, which are protoplanetary disks that are heated, and they show up in the infrared because they're close to these big stars. And they look for destruction of these proplids to see if they disappeared around big stars. And they don't. They do in fact exist. So they found absolutely no evidence that these big stars completely photo-evaporate away these very young protoplanetary disks that are forming close to these stars. So it suggests that planets do in fact exist in, they're being open clusters. Stars are born in clusters, and if a star like our sun, for example, happened to be close to a Type O star, there's been some suggestion that the planets would be destroyed, but there's no evidence of that. Apparently, planets do exist. They haven't actually detected planets as such, but they've detected the protoplanetary disks from which they form. So,
now,
as I say, good news for planets.
Yeah, I have a question about that.
Yeah.
The O-type stars are sort of the largest and shortest lived main sequence stars, right? So,
yeah,
by which I mean main sequence are sort of like most of the stars, right? And then there's a few stars that are either very old or very unusual that are not in the main sequence. But these stars have short lives, so and typically when they end their lives, they end them in a big explosion. So we're not going to see a whole lot of planetary evolution in the lifetime of a O star. We could see planets, but not, it won't get out of its basic early bombardment phase before it's blown away. But you could, the interesting thing is you could see remnants of that later, right? I mean, you could see bits of it in the debris in the dust cloud that forms around a nova or supernova.
Yeah, we're not talking about planets forming around the O stars themselves, but planets forming around stars close to them.
Right. Okay. I guess I was a little confused on that point.
I do understand what you're saying. If that Type O star is going to go on and explode as a supernova, that's not good news for any star systems that happen to be close by.
Right. Okay.
The jury's still out.
But I think that's an interesting result because it means that you have, instead of just evaporating, there's big solid clumps forming out there, which are gravitationally bound to themselves, which is interesting. They could even be like big Jupiters or something like that. So.
Yeah. Well, what astronomers need to do now is find planets, in star systems that lie within 0.1, say, of a parsec of a very big star. If they can find such planets, we know for sure that they're there.
Did you use the term photo evaporation?
Yep.
So is that all kinds of solar radiation coming off such a big hot star, or are we just talking about what is the process of photo evaporation? I guess that's my question.
It's mainly ultraviolet and X-rays destroying molecules. Yeah, ripping them apart, ionizing them.
Yeah.
So that nothing can form in terms of a planet size.
No, it'll be too hot. Far too hot for the molecules to coalesce into proper molecules.
Yeah, these are big white hot blue white stars that are blasting out a huge amount of luminosity. So they basically overheat everything. But what this new finding is that you can still form planets nearby, right? Which is pretty cool. There was another paper, was there, Adam?
Yeah, the other one that I read about was a theoretical paper, which I shall find the title of it. It's called Rapid. Oh, not that one, sorry. Hang on. I've got a list of them here. Where are we? It's about climate dynamics in tidally locked terrestrial planets. You may recall a few weeks ago we were talking to Pamela Gay, and you asked her, Paul, about specifically about planets around small M-dwarf stars. There's been a lot of discussion about whether or not such planets could be habitable. And this is important because they're very easy to detect, because red dwarf, M-dwarf stars are fairly dim. It's much more easy for astronomers to look to see a planet transiting across the face of the star, because there's a much more favorable star-planet contrast ratio. The planet stands out a lot better against a less luminous star. So planets are easier to detect around M-dwarfs. But we have to, because they're a lot less luminous than stars like our sun, a lot cooler, the habitable zone lies a lot closer in, somewhere around the orbit of Mercury in our solar system. So at that distance, a planet would very easily become tidally locked. And by that, it means that one side always faces the planet, has a permanent day side. The other side has a permanent night side, faces away from the planet. And that's not a situation that we're familiar with on Earth. It's not the sort of place that we would automatically think of as being habitable. It would be a very strange setup. You know, one side of the planet permanently lit, the other side permanently dark. And under those circumstances, some theorists have said that it would be rather hellish conditions because of the winds. You have what are called superrotation winds, whereby on the hot side, the atmosphere would rush around the planet to the dark side, cool, and then rush back again. So you'd have a constant flow of extremely fast winds rushing around the planet, and it would be fairly hellish. But this new study has found that that's not necessarily the case. They've done some very in-depth simulations and found that, yes, that could happen, but a lot depends on how fast the planet rotates and also how big the planet is. Bigger planets have faster winds, We know this because we've already looked at hot Jupiters, very big gas giants, and that is indeed what we see. You get what's called a Rossby wave, pretty much around the equator, which is, we have Rossby waves on Earth. That's what our jet stream is formed from. And this new study found that there are 3 basic type of climate models for these planets, terrestrial rocky planets that are tidally locked close in around M-dwarf stars. They can either have this superrotation wind, or it can split into 2. And under those circumstances, things will be a lot more stable. Or this wind could even split into 3. And under those circumstances, they estimate that it would indeed be quite habitable. So if this study is correct, I mean, it is only theory based on supercomputer simulations at the moment. There's no physical evidence for it. But it suggests that there's something like a 1 in 3 chance that these type of tidally locked terrestrial planets could be habitable. So, yeah, who knows? The next generation of space telescopes will tell us.
There was an episode of the PBS series Nova last spring and called Alien Planets Revealed that had some, if memory serves, some interesting graphics showing exactly that, a tidally locked star, a planet around a small red dwarf star, and how the winds would flow around it. So there's a nice accessible visualization of that if you haven't seen that show. Did you read enough in those papers about these supercomputer simulations to know if they took into account the possibility of oceans or large bodies of water?
They assumed an Earth-like atmosphere and an Earth-like planet. So they haven't varied the amount of ocean or landmass. They simply based it on the model of an Earth, a typical Earth-like planet. So, there's a lot more work to be done.
Yeah.
They did factor in quite a few different factors. It's quite an in-depth simulation, but they haven't modeled everything, I think it's fair to say.
Right. Think of how significant a large ocean can be in terms of climatology and changing the distribution of temperature on a planet and how winds flow. And even mountain ranges, too, can have a significant influence on wind flow around a planet.
That's right. Mountains give friction. You get an effect called friction dragging. Land masses flow winds down, oceans are flat, and winds to speed up. So, I mean, yeah, there's a lot more work to be done.
Well, there's a lot of variables, which I don't think you could account for in doing that kind of general study, right? Yeah, you're trying to find out what the broad strokes are. But yeah. keep in mind that
this is
the
first reasonable 3D attempt at modeling climate on an exoplanet. There's a lot more work that's going to be done in the next.
Well, we need some data, right? But the thing is that M-dwarfs are red dwarfs in general are something like 75% of all stars. So the galaxy is just flooded with these things, and if they can be habitable, then it completely changes the demographics of where life could arise. And that's something that's still under, this is one round of thousands of rounds of analysis that have to be done to understand that. And maybe the James Webb Space Telescope can look at some nearby red dwarfs and get some very detailed analysis of how they behave, and we probably won't be able to image planets, but it could certainly see the, get a good idea of the environment of that star. And but that's coming up in what, 2.5 years maybe. So we're not very far. They're making good progress on the integration test of James Webb. So
I happened to watch a hangout earlier on today, which was answering exactly that question, and apparently they're bang on schedule. JWST is apparently bang on schedule for launch in autumn 2018.
Right. Well, okay, keep in mind that something always happens. So, and they are completely willing to give way, let schedule give way in order to make sure that the mission is going to work. So this is one of those missions like Hubble, where performance is everything, schedule is not important, and cost is, just whatever you can get through Congress. And Hubble had tremendous cost, but they still got it through because everybody knew this would be the best telescope we'd ever had in many ways, and it worked out well. Yeah, the billions of dollars that were spent on it were considered a relatively minor investment, considering what we got back for it.
Yeah, just imagine how much Hubble telescope was a success. James Webb telescope is even more precise, more advanced. It is, just imagine the possibilities. Just imagine the pictures
Right.
it will send. I know it's not going to be seeing stars in a visible spectrum, but the pictures will still be amazing. I think it will be put more people, interested in astronomy.
Right. Well, I mean, the pictures will be good because it does have a visible light range capability, but its main purpose is to look very deep into space and see infrared. The things that are so far redshifted that they're no longer visible, and also things like debris disks, planetary disks, that are only visible in the infrared, will be very important. If you go to the James Webb Space Telescope site, they'll give you a list of the science they're really going to be looking at. A lot of it has to do with the very early universe, the most distant and faintest galaxies that are hard to see. Even what's happened since Hubble was launched is that there have been some enormously large ground-based telescopes that have been built, and they've solved, to a large extent, the problems that ground-based telescopes have of atmospheric distortion, speckling, that sort of thing. They haven't completely got rid of it, but they've gotten it way, way down to where it's not a big deal. And so the best images now are coming from the Keck telescope. And when the European telescopes in Chile come online, they will be just astonishing. You will get better pictures from that than you'll ever get from a space telescope, because you can always get a bigger light bucket on the ground. Yeah, it's just easier to do that for the same money. So the only exception would be if we ever start to build telescopes on the moon, then we could get bigger light buckets there. Costs money, but once we get the procedure down, I don't think it'd be that expensive.
Yeah, exactly. Because when you send the telescope into space, you don't get the destruction from the atmosphere. And imagine the telescope on the dark side of the moon. That would be just something incredible.
I've dreamed about that for 30 years, and I don't know how we're ever going to make it happen. But there are a lot of issues, a lot of challenges. But to me, they're just engineering problems, and you can solve engineering problems with enough ingenuity and time and money. The big question is that the people are going to ask you is how much time and money we're talking about.
Well, if ground-based telescopes get as good as you say, and it does seem likely that we can build bigger light buckets and adaptive optics on the ground, then that becomes the telescope on the dark side of the moon, and especially I would say the radio telescope on the dark side of the moon becomes what we can do in space that we can't do on the ground, and therefore a unique science mission that's going to return data that no ground-based telescope can return.
Okay, Nick, you just said a bad thing. You said dark side of the moon.
Sorry. My apologies.
Ladies and gentlemen, the far side of the moon.
Okay, the far side of the moon, in the shadow of Earth's electromagnetic output, and therefore radio quiet more than any other place in the solar system.
That's true. Yeah, that's correct. And also, an infrared telescope can be cooled to extremely low temperatures for many days at a time without a whole lot of active cooling. Passive cooling alone will suffice. So you could get integration times of 10 to 15 days in infrared without anything particularly sophisticated. Just because it's darn cold when the sun's not shining on it. And you could get I mean, you're right. The ground-based telescopes are limited somewhat by the atmosphere. They can never get. At some point, you're building a light bucket that's so big that it's collecting mostly atmospheric noise, but we're not there yet. They're talking about the overwhelmingly large telescope to go into Chile because they ran out of
strange names
of superlatives. They called it the very large telescope. Then it was the extremely large telescope. And then they had to go to the overwhelmingly large telescope because they were just, but at some point that light bucket is integrating a lot of noise. So it's going to be, there will be a point where the space telescope, if you can build, the problem is if you launch something on a rocket, right, and it's completely self-contained, it cannot be that big. And you have to figure out clever ways to unfold it and the James Webb Space Telescope is probably right now as far as we can push with our current rockets. With bigger rockets 10 years from now, maybe a little bit bigger, but not drastically bigger. So,
Hubble Space Telescope is operating for more than 25 years. So if we assume that James Webb Telescope will be operating for the same amount of time, and I think if we get bored with people on Mars, I think after 2040 maybe we get enough funds to send some telescope to the far side of the moon.
Right, far side. Thank you. Well, right, yeah, I think that the thing is that James. Hubble would not have survived as long as it did without servicing missions. It had a lot of failures. A lot of gyros blew out. James Webb, my prediction, and I do this for a living, my prediction is it will probably, given how carefully constructed and how much money's been spent on it, it'll last about 15, 20 years. It is not particularly serviceable, but if the only option is to spend billions of dollars to service it, they may do that. By that point we'll have robotic technology that we can just sort of tell it what we want it to do, and it goes out there and does it. I think
James Webb Telescope is going to be put in a bit further than Hubble.
Yes, it's at Earth Sun L2
Lagrange point.
Yeah, it's quite a bit further from Earth, a lot further from Earth actually. What it is it's the line that connects the sun and the Earth. It's on that line, along that line, or nearly along that line. That's a semi-stable point where you don't need a whole lot of fuel to stay there, and there is a line of communication to the Earth all the time. So it's and it's from the point of view of infrared astronomy. There's no Earth light to deal with. To speak of. There's no moonlight to deal with to speak of. It's all it's just sunlight, and they have this massive shield to block the sun, which has been a huge technical achievement, getting that shield designed and built. So yeah, they have. It will be way out there. Its distance is a part of a problem. The farther out it is, broadly speaking, the less mass of a robot you can build, right, to send out there. But with big launch vehicles coming online over the next 10 to 15 years, there will be it'd be possible to send a pretty good sized robot out there with replacement units and replace those units. Despite the fact it's not really that serviceable per se, like the Hubble was designed to be. Hubble was designed to be serviced by astronauts, by people. There were handles on all the units; they could pull them out.
No, exactly. And if it wasn't, send it to, if they send it and it wasn't serviceable, and then it wouldn't work, because when they sent it, they found out that there was something wrong with the lens.
Right.
And
it took multiple servicing missions, yeah, and it was a big deal, and it cost a lot of money, but compared to replacing it, it was pretty cheap. So, and they've gotten very good service out of it since then. They have replaced a lot of the parts and pieces on it since it was launched. And, I think most people would agree it's been a pretty good investment. I've seen
the best, probably.
I used to walk by that clean room every day where they did the servicing work, and it's one of the. I think it's the largest clean room in the world. It's huge. And now the James Webb Space Telescope is in there. Well, not all of it, but major components of the James Webb Space Telescope are in there. What they're going to do is they're going to put the major optical components on this structure, this gigantic optical bench. And they'll test those at Goddard Space Flight Center. I don't think they're going to test the entire spacecraft there because it's just too big. But the astronomy part of it will be tested there, the optical part, and that will be more or less isolated from the rest of the spacecraft. And the sun shield, which is so enormous, there's not a vacuum chamber in the world you could deploy it in. They'll have to test that in other ways. And
the James Webb Space Telescope webpage says it's the size of a tennis court, the sunshade.
Yeah, I've seen the full scale model. They had it parked up in the there's sort of like a small green space at Goddard when you first drive in the main entrance. And a few years ago, they had the scale model there with the sunshade, and it is very large. And I've never seen a vacuum chamber that could hold it. But you don't really need a vacuum chamber. What you need is, you need some way to negate the gravity so you can test its deployment. And the thermal analysts are very good. They can usually, with a little bit of validation, they can tell you how well a shield like that's going to behave, how it's going to perform. So it's going to be quite a feat. I have high confidence that everything will work. Hopefully, I think all the lessons learned from Hubble have been incorporated, and it's going to cost. It's a big chunk of NASA's budget right now, but it'll work.
There is another wide field infrared survey telescope, the W First telescope, waiting in the wings for the funding to come online after James Webb. Well, when James Webb is nearing the end of completion, NASA have said that they're going to devote some funds to the W First space telescope, which is good because they'll have two infrared telescopes in space then. W First is going to look at supernovae to try and measure the expansion history of the universe, and it will also be used for exoplanet hunting. they're going to put a coronagraph on it, which will block out starlight, so that they should be able to directly image exoplanets from Earth orbit. And I think they're going to try and do some micro lensing, which is another way of detecting planets. That's going to be a Hubble-sized telescope, 2.4 meter telescope that's being repurposed. It's been donated by the National Reconnaissance Office. It was intended to be essentially a spy satellite looking at Earth, and it's now going to be switched around to look out into space.
Yeah, I think
which is good for science.
Yeah.
Well, with all that infrared capability and the infrared capability of the James Webb Space Telescope when it comes online, presumably there will be more people trying to piggyback more infrared searches for Dyson spheres and the like, as we've seen with other infrared telescopes.
Yeah, I think you will see that. I mean, WISE, which was never meant to be used for any kind of SETI purpose, has been used quite a bit. And WISE is nowhere near as sensitive an instrument as WFIRST might be. I think it's also cool that the black budget has been tapped this way. Normally, the money that goes in the black budget never comes out, but this is interesting.
Well, we can hope. We can hope.
Yeah. Now, so where do you think? Let's sort of think about this. Where's the future of exoplanet hunting? We've got Kepler right now, which is been the big deal, but Kepler's going to go away before too much longer. NASA's talked about TESS. There's some European efforts underway to
Plato,
yes.
is, and Cheops is the other one.
Right. Plato is similar to TESS in its design. They look at nearby stars and they'll look at sun-like stars more than Kepler can.
What methodology do they use? Is it the same as Kepler with the occlusion of?
Basically yes. Yes, but they can look. They'll look over a much wider piece of the sky than Kepler did, or can.
Kepler stared at one patch of sky. Its original mission, it stared at the same about 100,000 stars continuously, looking for transits in an area of the sky close to the constellation Cygnus. TESS will cover the whole of the sky, looking at the nearest, brightest stars, looking for transits of planets across the face of the star.
Yeah,
they estimate that they should find around a dozen Earth-like planets, and perhaps up to 100 super Earth-sized planets. So it's exciting. I think that's due for launch in 2019, I think.
Mm-hmm.
Plato will, I think that's something like 2021, 22.
Yeah.
The future of planet hunting is pretty bright.
Yeah, I interviewed one of the scientists on the Plato mission last year. So if you, I'll put a link to that in the show notes. She explained it pretty well what they were trying to accomplish. The fact is that nearby stars, sun-like stars, will get a much better census with Plato and with TESS than we've had so far. And it's a more sensitive, because they're looking at more nearby stars, they'll look at a more sensitive detections. But it is basically, there's basically three methods, right? There's the eclipsing, where the planet passes in front of the star, and you see the drop in luminosity of the star. There's spectroscopy, where you get a very sensitive spectroscope on the star, and you measure the very subtle changes in velocity as planets go around it. And that's how the first planets were discovered. That's how Jeff Marcy does it. And they're getting better at that all the time with better spectroscopes. And then finally, there's this method where there's a very subtle gravitational lensing of a star, and if it's just right, it can actually make quite a bright increase in the luminosity of the star as the massive object passes in front of it. All these require a little bit of luck and a little bit of geometry, so they're all statistical sample. We can't survey every star that way.
So one of the interesting questions, from my point of view, is of those sun-like stars that are close to us, that are of obvious interest to us. How many of those planetary systems are going to be perfectly on edge to us, so we would see the planet pass in front of the stars?
Well, I think we know the number, the percentage, but I can't remember, quote it offhand. I think it's a few percent.
It's about 10%.
Yeah,
around 10%.
Yeah, I think that might be even optimistic, but
yeah.
Do
the other methods have a similar range of about 10, 20%, something like that?
Well, no, I think the spectroscopic method works over a much wider range, but you need a massive planet to see the variation in the radial velocity of the star. What you're looking at is the light from the star, and it moves in and out as the planet goes around it, and so there's a definite bias there towards big planets. Kepler's
Sorry, microlensing is just pure luck that you happen to have an alignment of two stars, one star passing in front of the other one, lensing a background star. That's just completely fortuitous. I don't think you can put an estimate on how many, what percentage of microlensing events you might see. It's just pure luck that you happen to be looking in the right direction at the right time. Simple as that.
Right.
I don't get many of them.
What Kepler has done, which is the big achievement, is they have pushed that one method down to Earth-like size planets, and they've learned an awful lot in the process of doing that. And so that missions like Plato and TESS will be able to learn from all that and do even better. And because we have seen I don't think we've seen anything Mars size at all. We're pretty sure they're out there. We just haven't seen them because they make such a tiny dent in the luminosity of the star.
There's been one.
Oh, there probably is. Yeah, I think I do recall one.
Yeah.
And they don't tug a star around much by their gravity because they're small.
No. It's really hard to detect something Mars size. You have to be kind of lucky.
Timing variations is the way that the smaller planets can be detected. If you can see one or two planets transiting in a multi-planet system, they don't always transit at exactly the same time. Like the Earth goes round the sun every 365 days. Well, I know it's not exactly that, but roughly. In some planetary systems, the timings are off slightly because other planets tug at them. So astronomers can infer the existence of planets they can't see by that method. Not easy. And of course, you have to wait to see the Earth from a distant star system. You'd have to wait 365 days to see it. You'd have to see it transit twice. You're talking about waiting 2 years. So it takes a long time.
Yeah, I think it was even more than 2 years. I think if we're speaking about Kepler, I think it was 3 or 4 years to get the planet confirmed. I think, and just 4 years after Kepler running, I think we got the first Earth-like planets. But the smallest planets, I think in the term of astrobiology, it's not interesting point because it's very hard for life to exist on those planets because, like on Mars, the inner core is already stopped. It's cooled down, and the life couldn't, exist there. So
Yeah.
speaking of astrobiology, it's not the interesting point.
Right. Well, I mean, between Earth and Mars, there is kind of a sweet spot where, you might be able to get a habitable planet, and but the fact that we haven't seen many Mars-sized planets is just an indicator that there is definitely a size bias, and no surprise to that. Everybody thought there would be, but
is there reason to believe that a Mars-sized planet could not have, or would be unlikely to have, plate tectonics, or to be geological active? Because we know some of the moons of Jupiter are very geological active in terms of volcanism, although whether or not they have plate tectonics, I don't know.
Well, they have a different energy source, but Mars had no energy source, right? It had nothing to drive it, and so it just blew all its energy out through volcanoes, and it was done.
But is there reason to believe that a Mars-sized planet could not have an active core and enough decomposing radioactive elements in its crust to keep it warm for a period of time?
Yeah, I think there are people that model that. It again, lots of variables, but yeah, a planet that small cools off really fast, and the heat just gets out quickly. And the plate tectonics, I think they still don't, there's still only n=1 there. There's a lot of discussion about what initial conditions you need to get plate tectonics. Do you need a lot of water? Do you need, what kind of composition do you need? That's an ongoing point of contention.
You can never say about small planets, about plate tectonics, because you can never guess what you can find, because no Horizon, when it passed through Pluto, they were scientists were stunned because they found actually some recent geological activity. You don't suspect something like that from a planet orbiting so far from the star, basically a cold ice ball. And they found mountains, high mountains, and then I think they suspect that there were some recent. When I speak recent, I mean 100 million years or later. Technological, plate tectonics.
Yeah, that's true. I mean, Pluto is tiny, and yet we're still, it was a big surprise. Nobody really expected that. There shouldn't be anything driving its activity. So we still have a lot to learn. And I think that Pluto is going to constrain a lot of theories. So the problem is, that we know there's not plate tectonics on Mars. We can see that very clearly. We think there's probably not plate tectonics on Venus. But Venus has been extremely active, but it's all volcanism. So that's all we have to go on. We don't have a whole lot of data, and it'll be a long time before we do. So
it would be interesting to find a Mars analog very early in its history. If we can find a Mars-sized planet that's very young, that would be interesting.
Yeah,
what it looks like.
I totally agree with that. Yeah, I would.
I think one of the things what we're beginning to find is that there's an incredible amount of diversity to planets. There are very different worlds out there that we just never dreamed might exist. Carbon planets, ocean worlds, steam planets. Who knows what we might find? That there's going to be even diamond planets might exist. There's going to be an incredible amount of variety. So, it may take a very long time to find anything that looks like Earth. Those in a galaxy of what, maybe 100 billion, 200 billion stars. There's bound to be one somewhere in this galaxy, at least one. There's bound to be, who knows, 100 Earth-like planets, 1,000. We don't know yet.
Yeah, we can't see most of them yet. I mean, they're too far.
But even things that aren't Earth's twins, but relatively related, large. What do they call them? Large, not large Earths, but something like that.
Super Earths.
Super Earths. And they're all going to have a lot of interesting features and phenomenon to reveal to us. So what I'm saying is we shouldn't get too hung up on the idea of finding a perfect Earth twin. That'll be interesting, but the other planets are interesting too.
Well, there's been people who have been saying there's going to be an Earth 2.0, which is kind of an odd term, soon. And every once in a while, one comes up that's pretty close, not quite there. And again, I would refer everybody to Abel Mendez's website at University of Puerto Rico, where he maintains an Earth Similarity Index. And you can go there and look at the Earth Similarity Index of confirmed exoplanets and see which ones are closest. I'll put a link to that in the show notes again. Abel and his team do really nice work there on the website. And you can see for yourself how close some planets have come. And this is all based upon, nobody's actually taking a picture of these planets. You'll see little artist conceptions of the planets, but they're not. What they really have is either a spectrum, or they've got an eclipse. The method they use, where the planet passes in front of the star multiple times until they can confirm that it's there. You have to be lucky with the geometry there. Most of the planets that are out there, we can't see by any of the methods we have. And so we're especially the Earth-like planets. So we still have a long way to go. And there could be one just 10 light years away that could be a perfect Earth analog, but we wouldn't know it. And there's not that many stars within 10 light years. So,
but if only 10% of the stars are available to us by the transit method, planetary systems are available by the transit method, yeah, there could certainly be a very close Earth analog within 10 or 20 light years. We shouldn't be surprised by that.
No, the problem is how we're going to find it. And that's really, not even the next generation of telescopes. Is probably the generation after that, where we could start. There was a plan to build something called the Terrestrial Planet Finder. It cost a little bit too much money, and so to make room for things like the James Webb Space Telescope, it was put on the shelf. What it would do, it would be a very sophisticated, tricky mission to actually block out the light from the star. You could actually see planets going around a star. That's very difficult to do in space. We do it all the time in the ground with things called coronagraphs. We're just blocking out the sun. But blocking out the sun is relatively easy. Blocking out a very distant star is much more difficult because its angular size is so tiny. It's sometimes you can see that when like an asteroid or a planet or the moon passes in front of a star, but you only have seconds to do the observation. It's not enough time. So that will be something that will, we can maybe fund that in 10 years, 15 years.
Do missions like that get dusted off and pulled down off the shelf?
Yeah, but the technology will have been completely reconfigured in that time. So you'll probably redesign it.
So when you say it's two generations of technology away, what do you put as the approximate length of a technological generation?
Well, for telescopes, it's typically about 20 years.
So about 40 years from now, then we'd be looking at imaging exoplanets with the technology we would available.
Earth-sized exoplanets, yeah.
Yeah, we actually detected 60 planets by direct imaging, but it's all, bigger than Jupiter, like 6 masses of Jupiter, 7 masses of, even bigger. The smallest I think we found from direct imaging was like 4.5 or 4 masses of Jupiter. So it's a big planet.
And that was very cleverly done, I must say. But you have to have the right combination of planet and star to do that.
It's very early days.
Yeah.
The Gemini planet imager. It's only been going since last autumn. Not even a year. So give them a chance.
Yeah, I just think that in terms of a useful image that we can actually take a spectrograph from, it's a long way off. And because what we need to be able to do is not just take a picture of it, we need to be able to, that's a few pixels wide, we need to be able to actually analyze the light coming from it.
I dream about the time when we actually read the news and the picture showing the planet would be actually this concept like we see it now.
Yeah.
That would be nice.
I'm not sure I'm going to live that long. Maybe you will. But yeah, that would be beautiful. And that's, that will be long before we can actually send a probe there. We'll be able to see the planet with a good telescope. Maybe on the far side of the moon.
Or in precursors to interstellar missions, like if you are sending a probe to the focal point of the sun, 542 AU, perhaps that would give us a perspective that would allow us a planet hunting spot that's better than close into the Earth.
Well, maybe. Those kinds of things require a little bit of luck too, but I think that there has been talk about sending probes very far from the sun, primarily to get a better parallax or get a better interferometry. But there was even back in the 70s, there was something called the 1,000 Astronomical Unit mission. That was actually quite a good design, but it never happened because of the cost, of course. These things don't get, the vast majority of these good ideas don't get funded. Of course, we like to think none of the bad ideas and only a tiny fraction of the good ones get funded.
Well, a lot of those ideas are risky because they involve things that haven't been done yet.
Oh yeah, you have to do a lot of technology development in other cases, which is why NASA put in the innovative advanced concepts. They said, well, let's isolate those things that need a lot of technology development, and we'll recognize that that's a necessity, kind of like DARPA has done. DARPA says, look, there's stuff that we can do now that we're not interested in, and there's stuff that we can do in 5 years that we're not interested in, and stuff that we can do in 10 to 20 years. What do we have to develop in between then to make that real? And, that's the IAC has been all about identifying those technology needs. But of course, technology tends to sweep along, driven by commercial needs, as much as by NASA's needs or the Defense Department's needs.
But it also grows in unexpected ways.
Yes, it does.
Way back when, before the exponential increase in computer technology, people thought of better telescopes as bigger telescopes, and now older telescopes, well, not really old telescopes, but they are being refitted with computer gear and sensors that make them much more sensitive than they were in the past. Sometimes it's almost like getting a new telescope when they put the really sensitive electronics onto the 200-inch telescope or something like that.
Yeah. Well, that's true, but still a bigger light bucket is still a better light bucket if you can control it well.
Yes, if you can control it well. But apart from straight up technological innovations or breakthroughs that would give us better planet finding characteristics or better missions, a couple people at the Starship Congress I was at earlier this month that mentioned that there are people playing with the idea of gravitational trajectories that could accelerate things. Properly inserted spacecraft could be accelerated significantly beyond anything we've done so far. So that doesn't necessarily require better technology, but it requires a lot better science to figure out how to do that. Just being clever about how you do a gravitational assist around the sun.
Right. There's been also I don't really want to get into SETI right now, but there's been discussion of using gravitational lensing by the sun to focus radio waves as well, or actually almost any massive object. But anyway, and that is clever, but it also rather constraining. I think Chirovilla has a question or two. Let's see. Go to the questions. Or maybe it's a comment. Let's see. Chiro said, think of the fascinating evolutionary history of a theoretical, non-technologically advanced alien species living on one of these planets and evolving on the dark side. I'm presuming that we're talking about the around the M-dwarf. And how their adaptation to darkness would make them evolve specialized sensory. Anyone want to take that?
It's a fascinating thing to imagine, isn't it? How life might evolve in darkness. Would they have eyes? Would they use radar? It's...
Well, we kind of have that. We have life that didn't originate in darkness, but maybe we see that in the deep ocean, right?
And in some cave life where animals have gone and lost their eyes.
That's right.
You have fish that have little lights hanging from their noses, right? They can hunt.
The anglerfish.
That's fascinating.
Yeah, the anglerfish.
There's bioluminescence in quite a few science fiction films I can think of. Avatar. There's a Star Wars game with a world very similar to that we're talking about.
Pitch Black has bioluminescent life.
Yeah, it does. There's probably dozens of. Yeah,
I was gonna say it happens often enough in nature.
Imagine.
Yeah, maybe it wouldn't be a non-technological species. Maybe it would be a pretty sophisticated species. They would still have access to electromagnetic radiation. They would still have access to all kinds of other energies. So,
interestingly, the examples we can pull up of life adapted to non-light conditions on Earth are in the depths of the ocean and in caves. So the interesting question here is, life adapted to non-light conditions not in the depths of the ocean or not in caves. So ordinary land-dwelling animals adapt with bioluminescence. Well, I guess we have fireflies. Fireflies are bioluminescent, and they are flying invertebrates, as it were. So one would suspect something like that in a completely dark environment.
Right. Well, you see that there are nocturnal animals that are very good at surviving in low light, but there's bioluminescence to solve different problems. Like the fireflies, I think primarily use it for getting girls.
Yeah, it's primarily a mating signal, and different species of fireflies have different flash patterns, different appearances of the light. Some of them look like a J, some of them look like an H, and it kind of segregates different species that way too.
Yeah.
But it can also be used to, like with the anglerfish, attract food. I don't think they use the light so much to attract mates, because the anglerfish you see are actually all female. The males are just a little, looks like a cancerous growth on the side of the female.
Oh, it's kind of like humans then.
Sort of. But I was also thinking on the exoplanet, life on a tidally locked exoplanet, they would almost have to develop along the meridian between the daylight and the sunlight side, or daylight and the dark side.
That's exactly what I was thinking. It's fascinating to think about a permanent terminator line. But we're so used to the terminator between day and night, constantly moving around our planet. On that planet, it's stuck in one particular place forever. It would hardly ever move.
You would expect to see extremophile species adapting both on the light side and the dark side, stretching out from that ring of life that would go around the meridian.
Yeah, and the atmosphere would mix things well enough that there wouldn't be a sharp cold line, warm line. It would be, but it might be some interesting weather.
Yeah, I'm thinking they'd almost have to be subterranean or cave dwellers, because you'd have, Coriolis winds just ripping along through there also. Probably not an avian species.
If you had a tidally locked planet, like we've been talking about around a red dwarf, but it had a moon, would that moon give a small amount of illumination on the dark side on a cyclical basis?
Yes, it might very well.
So you would have species adapted to extremely low light conditions and a cyclical, depending on the size of the moon and its orbit and its orbital characteristics, would give a greater or lesser amount of light.
No, I think we have a good chance to find such a life, living in the dark on the planets orbiting, red dwarfs. Red dwarfs are, live much longer than our sun. Actually, they live for, 10, 15, 20, or even more billion years. So the life has the time to evolve. So we have better luck finding life there.
Mm-hmm.
Well, even if they're completely sightless, though, they can still get around. You look at a person who's never had sight, can't even determine light from dark. They can teach themselves to get around. There's a few guys who have taught themselves echolocation. So it may be a species that entirely relies on echolocation also, instead of bioluminescence.
Yeah, one would expect to see various forms of sonar or any other organs that could be evolved, tapping into whatever electromagnetic radiation could be reflected off any other surface. It gives you an opportunity to some analog division would be possible with many different frequencies.
Well, there's always infrared. I mean, it's not freezing there, and there's what we found is that on Earth, vision has been invented many times by lots of different branches of the tree of life, because it's such a huge advantage to have. So, if light in the visual spectrum isn't available, light somewhere, something else will be. Some other form of energy that has information in it about the environment will be there.
Definitely.
And and you don't necessarily have to be blind to develop, sophisticated acoustical problems. Dolphins can do all kinds of things with their sonar, as can bats. And bats are not blind; they can see just fine.
Yeah. So it's just they've learned to use their echolocation to distinguish between an insect and a falling leaf, or between other bats, and even send communicative signals saying, avoid this area or come here. But like I said, sight isn't always the only but they could be an entirely tactile species also.
Right. Yeah. Bats are pretty much my favorite animal after ligers.
I'm partial to ferrets.
Have you ever lived with any?
Yeah. And my great grandmother used to have, I think, up to 10 or 12 of them at a time.
Oh my God.
They kept rats out of the hay barns.
They do that, yes.
Yeah, these were trained ferrets.
Uh-huh. Well, okay, guys, we're going to wrap it up pretty soon. We've talked mostly about exoplanets tonight, which is cool, because exoplanets are a hot topic. We are in a golden age of exoplanet discovery, and I think we agree that it's going to get better. It looks like that new missions are coming online. Patrick Festa mentioned that there's something on the drawing board called the Light Blocker Project, which Sarah Seeger's involved in, which it would be basically a technique for blocking light so you could image planets. So that's something that is being actively thought about all the time. The Terrestrial Planet Finder was that as well. And possibly after James Webb goes up, the Terrestrial Planet Finder will find a home in the budget. It'll be a different design. It's kind of like, or it might go to, the Europeans might do it, or the Japanese might do it. I mean, look at LISA. LISA was a NASA project or at least a mostly NASA project for a while. Now it's a European project. It will take longer, but its purpose is to detect those very long wavelength gravity waves, which the current gravity wave detectors cannot really see that clearly because LIGO is just starting up. It should see gravity waves of a certain size, but the really ancient gravity waves that are from the early universe it may not see. So that's something that Lisa could actually give us new physics. That kind of thing is happening, and probably in the next 10, 15 years, we'll see a lot of progress. And by the way, we don't talk about LIGO, but we're going to need to get an expert in to talk about that. LIGO is just starting up again, and it's a big deal. We did talk a little bit about it with Ben Tippett on episode 1, but we need to get somebody from LIGO in here to tell us what's going on with that. It's really an exciting project. And they should be announcing something in the next year or year and a half, something like that. So let's go around one more time. Just unmute your mic if you want to say one last thing, and we'll wrap it up.
I was just thinking, I belong to an organization called SaganNet, which is an astrobiology project. It would be nice if we can get an astrobiologist to come and talk to us one time about some of the topics we've just been discussing.
Yes, it would. I agree with that. And in fact, I had, I did find an astrobiologist from SaganNet once for the WOW signal with Mateusz Macias. And she's not an expert on exoplanets. She's more of a chemist and microbiologist, but she was great. That's a good point. We could dig into that. There's a lot of talented young scientists in that group, and they actually have a conference on astrobiology where only young scientists are invited. Which is graduate students, postdocs. No senior faculty, and
even like me.
Yeah, and what that does is it takes some of the usual politics away and lets them just talk about their research. So good suggestion, Adam, and we'll follow up on that. Anybody else?
You mentioned earlier in this podcast Abel Mendez. Have you tried to contact him and see if he'd be willing to come on and talk?
I have interviewed him for the Wow Signal
Uh-huh.
last year. I would like to follow up with him at some point on the latest discoveries. I'm kind of waiting for those to accumulate. But yeah, the Unseen podcast, maybe he's in Puerto Rico. He's kind of the same time zone I am, so could happen.
Another idea for a possible future Unseen podcast, since we were talking about kind of projects that could be pulled off, have a round table and asking people if they had 10 or 20 billion sitting around that they weren't doing anything with, what would be your favorite fantasy science project that you would spend it on?
That's a good idea, actually. If you had as much money as, say, the Large Hadron Collider had, how would you spend it?
Yeah, exactly.
Or no, the F-35 jet, which doesn't work. If you had that much money, Death Star. That's a good idea, James.
What would its science mission be?
How fast do planets disintegrate when you hit them with a death ray? I want to know that.
See if other planets actually have a liquid core.
They can sort of strip it away layer by layer and see what's in there.
That would be
my
interesting.
fantasy.
That would be interesting.
My fantasy space mission would drop off it would drop off a probe at Europa, go on to Enceladus, and then go into your orbit around Uranus. That's what I'd do with it.
I would drop a spaceship on Europa, dig into the ice, and just leave some like a submarine and find out. And I think we could even find us some life, some fish swimming there.
Well, yeah, could be. Yeah, well, one thing I want to do is we have like 3 published science fiction writers in the community, including one of my favorites. And so I would like to get them to speculate on, what would a very, very advanced technology look like. I know they've been thinking about that. I want to see the results of their work. Certainly, Dr. Benford has been thinking about that quite a lot over his career. But we also have Laurent Planer and David Grigg. So that would be a fun episode. Forget what if you had $25 billion. What if you had $25 trillion?
Indeed, that raises the stakes, makes it look more interesting. Then you really could build a Death Star.
Well, or you could make enough antimatter to go do an interstellar mission. That sort of thing.
We have a Death Star in our solar system. Actually, I think it's a moon Mimas.
Yeah, it looks like the Death Star. Yeah,
it looks like the Death Star.
Yeah, it has that big crater in one spot.
So we don't have to build a Death Star. We actually have to.
I don't think there's that ventilation shaft that you can fly down into, and yeah, if you use the Force. Okay, we're getting way too nerdy here. Even for me. Anybody else? Final thoughts? No? Okay. Well, I just wanted to mention a couple things that are coming up. Next week, Friday, we will have a meta episode where we will talk about, there'll be a podcast about the podcast. I promise you we won't do that very often, but we will do it next week. We'll talk about the first 6 months of the podcast, what we liked best, what we didn't like, how we think it can be better, and so on and so forth. Good memories, bad memories. Panel for that is not set yet, but hopefully soon it will be. If you're out there listening and you know that you're in the panel pool, why not volunteer? If you want to be in the panel pool which is basically anyone who's eligible to be on a panel for the Unseen Podcast, just email me at unseenpodcast@gmail.com and we'll set you up. It's not really that hard. It just uses software that everyone has access to. Won't cost you a penny. The other thing is, I wanted to mention that episode 27, which is 2 weeks from today, will be the Mars One rebuttal. We'll bring in people from Mars One, let them have their say about what they think the strengths and weaknesses of the Mars One plan are. Let them talk about the debate between MIT and their CEO. Let them talk about why they chose to become Marsonauts and what their hopes are for that. I think it should be interesting. We may not get to the truth about whether Mars One has a good plan or not, but we may get to the truth about the human factors involved, why people want to do this, and what their dream is, what they expect to accomplish if it all happens. So that's good. Now on March 28th, I think, not March 28th, episode 28. Adam will probably be the host. At least that's the current plan, and that's wide open is what the topic will be. But it'll be a bit earlier in the day for those of you who find our particular time a little bit taxing for whatever reason or other. People have already signed up for that one, so we are already starting to form a panel there. A bit later in October, there will be a cryptids episode where we'll have some fun skeptically considering the notion that there may be giant man beasts running around the forests in North America or whatever. I'm not an expert in that area, but we're going to bring in some people who are. It'll be fun.
How do you become an expert in Sasquatch?
You go squatching.
You eat a lot of that jerky.
You drive your pickup truck around the boonies of North America for many years.
Yep, or just do like I've done and creep through the woods.
You have woods? Anyway. Because I've been in Oklahoma, it was like you can see for miles. There are no woods.
We've got elk populations. We've got black bear populations. We've got there's some wooded areas. Depends on which part of the state you hit.
Okay. Well, let's see what else. That's pretty much the whole plan for now. There's a whole lot of episodes up ahead that we don't have plans for. If you have ideas, thoughts, comments, questions, let us know. Episode, like I said, episode 28 still wide open. So was episode 29. So we could have special guests on. As people here have suggested, we should get somebody from lots of different fields. Somebody from LIGO would certainly be a great idea. If you have any ideas like that, or you know somebody, they owe you some money or whatever, have them contact us, and we'll get in touch with them and set them up. We'd like to have a special guest every 3 or 4 episodes, somebody who can keep us straight on the facts and answer our questions. So it'd be great. If you have anything else, just email unseenpodcast@gmail.com. You can go to our blog at unseenpodcast.com. There you can comment on episodes. You can make snarky remarks about how ugly we are or whatever you want to do. We'd like to hear from you. Really, we would. We're also on Twitter at Podcast Unseen. We don't have a Facebook page yet, but that's something that's in the planning. And maybe we'll have one in a few weeks that you can go visit. So please subscribe to the podcast if you get a chance. Just go into your favorite podcatcher or what software, whatever that is, whether it's on iOS or Android, or on your desktop. We're on iTunes. You can go to iTunes and find us and subscribe there as well. So we look forward to seeing you next week for the Met episode, where we talk about what we talk about. And this is episode 25 of the WOW Signal. It's still here on the East Coast of the United States, the 18th of September 2015. I'd like to thank our panel, Adam Synergy Smith, who's up very late in the UK.
I've now been awake for 21 hours.
Oh, you're about to go to bed.
It's been a pleasure, though. I always enjoy it.
No, you did a great job, Adam. Thanks. James Garrison from Oklahoma.
Yep. Been a lot of fun, Paul, guys.
Mateusz Macias from Poland.
Yeah, thank you guys for the episode.
Mateusz is also up ridiculous hour, should point
exactly. It's 5:30 a.m.
And Nick Nielsen, who's up at a reasonable hour in Portland, Oregon.
Thank you once again for being able to participate.
Yeah, thanks for coming in late. We had a no-show, as we often do. And this is Paul Carr, and your host, and I appreciate you guys listening. Thank you for listening. And check us out at unseenpodcast.com, where you can find all the episodes to download, listen to, whatever you want to do. And we'll see you next week. Goodbye.